All right, let's have a quick look at this. I'll include in this bit here as well. So we've got, imagine a ball falling, 100 joules of gravitational potential energy. It's the maximum kinetic energy is going to be 100 joules of kinetic energy because it's just converted one to the other. And as we said earlier on, when we looked at conservation of energy, energy cannot be created or destroyed, and so the gravitational potential energy you cannot get 100, you cannot get more than 100 joules. You could get less, but that wouldn't mean that energy is being destroyed. It's just you probably also produced heat energy or thermal energy. So the question you got now is essentially, how does the velocity, what happens, how does the kinetic energy relate to the velocity? Well, the formula for kinetic energy is equal to half times the mass times the speed, which we're just going to give the same symbol as velocity, squared. Okay, these v's look a little bit like r's, but you got this like little line. It just tells you that it's lowercase r. If it didn't have that, like that, it would basically mean it's uppercase r. Anyway, so that's the equation. Now this means that the kinetic energy is directly proportional to the mass. So in other words, if I keep everything else the same, the velocity the same, then if I double the mass, I double the kinetic energy. And you can also see, if I kept the mass the same, that the kinetic energy is directly proportional to the velocity squared. So if I double the velocity, it would not double the kinetic energy. So it would quadruple it. It would multiply it by the scale factor would be squared. So if I doubled it, this would quadruple. If I tripled it, this would multiply by 9. If I multiplied v by 4, this would multiply by 16. But to prove that, without just going, okay, I sort of can visualize that, but sometimes we want a little bit more evidence. Let's start off with an example where the mass of this object is, we're going to keep the mass the same. We're going to keep it nice and simple, 1 kilogram. Okay, so you end up just multiplying it by 1. So the kinetic energy, in fact, it could even be, the kinetic energy is equal to a half times 1. And we're going to say the velocity this time is going to be 2 meters per second, so 2 squared. So you can see it's going to be a half times 4, right? 2 squared is 4, so that's going to be 2 joules, right? Now we're going to change it. We're going to say the kinetic energy, we're going to double the kinetic energy, so we're going to make it up to 4, so half times 1 times 4 squared. So 4 squared is 16, and then half times 16 is 8. So 8 joules. And just like I said, when I doubled the kinetic energy, when I doubled the kinetic energy, the velocity quadrupled. Okay, so it didn't just multiply by 2; it multiplied by 4. Let's do a similar thing. We'll triple it from 2. So we'll say, imagine the first one was 2, and we'll go up by multiplying it by 3. So half times 1. So multiply 2 by 3, that's 6. 6 squared, oh God, what's this? It's 36, isn't it? Is that right? Your 6 times table? Right. 36 divided by 2, so that's going to be 18, isn't it? Is that right? Yeah, 18. So 18 joules. Okay, so if you have a look, so it's 2 to 18, that's 9 times the amount. Again, when I tripled the kinetic energy, when I tripled I'm mixing up these two, I think. When I tripled the velocity, the kinetic energy went up by 9. When I doubled the velocity, the kinetic energy went up by fourfold. Okay, so the scale factor itself is squared. Okay, does that make sense? Okay.